So first, thanks to all the organizers. It's always really, really nice to be here. The place is really great. It's always a pleasure to be here, resting or presenting, depends. So today I'm going to talk about Monte Carlo diffusion processes. And before maybe getting to the details of these frameworks, I'd like to say that it's a joint work with Eric Moulin, Yazid Janati, and Gabriel Cardozo from École Polytechnique. And I would like to say a quick word about this because it's a work really done by Yazid and Gabriel. So you saw them yesterday and you're going to see them another time on Thursday, I guess, for the tutorial. So they don't have the opportunity to present their own research work. They are only working for you with this JAX tutorial. So I'm working for them now. And what I'm going to present is really their work, the last work they did during their PhD. And they were really advised from quite far away from by Eric and myself. So if I say something wrong, it's on my side, but every good part are from them. Monte Carlo guided diffusion. So maybe before getting into the details and displaying data and everything, just a few words about what I'm going to talk about. Bayesian inverse problems. So we're going to have observations on data, and the main target of the talk will be to estimate the posterior distribution of the data given the observations. And one thing we're going to do in the talk is that we won't make any assumption on the prior distribution of the data. So we won't try to assume anything on them. So before solving the Bayesian inverse problem, the posterior law estimation, we will have first to estimate the prior only using data. And this is the reason why we're going to focus on diffusion processes which have been designed for this for the past, I don't know, 2 or 3 years. And once we've done this, so we could estimate the prior with many tools. We decided to use diffusion processes because they are really efficient. And then we're going to use the diffusion processes framework to go on and estimate the posterior distribution. So diffusion processes have been widely used, especially to sample images. So all the initial papers were designed to sample images, so learn a distribution on data, which are complex here, so quite high dimensional images, and then the target is to sample new data, new images. So here you've got a sample on the data we didn't use for the paper. I didn't want to display only pictures of celebrity, which I don't think is really interesting. This is a data set that we've been working on with Pierre Glohagen and Mathis Chagneux, which are video shots from riverbanks, and then we retrieve images and try to detect plastic waste in these riverbanks. So you should, when we talk about data, you should think about this kind of data. So these are not the one the models have been trained on, but this is the same level of complexity, I guess. And what I said before is that, so we've got RID samples, so these are these images, and we assume that there is a generative process behind which generate them, which is denoted by the distribution pi0 that we don't know. And what we're going to do in the talk is to split the talk in 2 parts. First, there is a parametric estimation of the data distribution. So here we're going to just follow the path of what people did in the Monte Carlo diffusion processes. So we're going to use a parametric form for p theta, which will be an estimation of pi0, and estimate it, so not directly using a maximum likelihood. So the initial paper was written by estimating p theta using a variational inference, but there are many ways to do so. I guess the models we're going to use have been trained using score matching, but we don't really care about it. What we're going to do is estimate pi0 using p theta in the first part of the presentation. And then we're going to try to estimate another law which depends on pi theta, which is it can be seen as a posterior distribution. So if you assume that you've got an observation y with density conditional to x given by g, then the posterior law of x given y will be proportional to g times p theta. So you're going to try to sample from this kind of distributions. So here and hopefully in the remaining of the talk, theta star will be the parameter theta you get once you've estimated the prior distribution. And what I call prior is only the distribution of data. Slides were terminated like 10 minutes ago, so maybe notation won't be really coherent all the way through, but hopefully you're going to get everything. So G can be seen as a reward function in reinforcement learning, but in our case, it's really going to be an observation model. So we're going to try to focus on posterior sampling. And an example of what we're going to do. So during the talk, I'm going to strictly focus on the Bayesian linear inverse problem. So we're going to assume the function f here is linear for most of the talk, and I will explain why at some point. But basically, I guess everything that I'm going to say can be extended to nonlinear settings, obviously with a bit of work, but the methodology should work in these settings too. So we've got x, which will be sampled from pi 0, and we've got an observation y, which depends on x through these kind of models. And here you can have examples of what we can do with it. Here you've got a noisy observation of fluorescent microscopy data. Once you don't have access directly to it, you only have access to this kind of blurry data. And what we try to recover are those samples, which kind of look like this guy. So this is what we're going to do now. The other way. So what we're going to do is, first I'm going to try to describe diffusion models. So the idea is quite simple. The methodology is easy to understand if we don't go to the details. So I'm going to try to do this. And then the new part, I guess, of the talk is our step 2 and step 3 is one we've estimated P0 theta star, how we can use the same framework to sample from our posterior distribution. So I'm going to spend like half of the talk talking about this. So if you already know diffusion models, you can just raise your hand to go faster. And then just nothing really new about the Monte Carlo method we're going to use here. So what we're going to do is use what Nicolas explained this morning and yesterday. So we're going to use standard SMC procedures, but in the settings of Monte Carlo diffusions. So let's go for this. So why is it a challenging problem? So G0, so you should remember this notation is important and should be kept all the way through. G0 is a conditional distribution of y given x. So in our case, it's a linear Gaussian model. So it's a Gaussian centered at a times x with variance sigma square. And we want to sample a distribution which is proportional to G0 times P0 theta star. So this is the first part where we twisted the problem. We should sample from G0 times P0, but we don't know how to do this. So first, we are going to focus on a biased problem. And we won't talk about the upper bounds on how we can control the error we are making doing this. This is an open problem. And what are the problems here is that we don't know with diffusion processes how to evaluate P0 theta star. We only know how to sample from it. So these are the constraints we're going to work with. Diffusion models now. So this picture was taken from Yazid Janati's PhD defense. This is a nice puppy that to explain the complex problem of diffusion models. So what you're going to do is, first, you have access to data which have been sampled through pi 0. So you can sample x0 from pi 0. And then what you're going to do is take this dog and blur it sequentially until you obtain just random noise. So you can do this with many different processes. What people have been doing in diffusion processes is only using linear transformations and adding Gaussian noise. So what you can recognize is that you're going to sample from x0, you're going to sample a Markov chain, which is a discrete time Einstein-Uhlenbeck process with stationary distribution given by the standard Gaussian. So what you're going to do is simply, using this Markov chain, blur the data until you obtain this random noise that we're going to assume is sample from standard Gaussian distribution, because this is the stationary distribution of the Einstein-Uhlenbeck process. So pi 0 is a true distribution of data, and at each time k, we've got pi k, which is a convolution between the initial sample and the Gaussian moves you make at each time steps. So we don't know how to evaluate this quantity, because we don't know pi 0, but we know the conditional distribution of xk given x0 at, for each k, it's a Gaussian, given by this square root of alpha k and 1 minus alpha k here. So these are standard computation. Okay, so here what you can, what you can write is the conditional, the joint law of all the x's you've added noise to given x0, which is a joint distribution, which is a joint Gaussian. And what you can remark is that you can decompose this joint law in a backward fashion, just using bridges, using the law at each time k of xk given x0 and xk plus 1. So this is this quantity. So k the law of xk minus 1 given x0 and xk in this case. You can write your joint law using only this distribution here, and you can compute this quantity explicitly. You know that it's a Gaussian because we've used an Einstein-Uhlenbeck process. And you end up for this distribution with a law, which is a Gaussian with mean, which is explicit in xk and x0. So the important part is that at each time here, your Markov kernel depends on x0, which you've sampled from. What we're going to do now is try to estimate pi 0 by introducing a joint law, which is going to mimic this decomposition. So we're going to use a joint law for x0 up to xn by using a backward Markov chain, which with initial distribution here, standard Gaussian. And here we're going to propose a Markov kernel which goes backward in time with a Gaussian distribution and a mean and variance, which are thought as mimicking what's happening here. So what we want to do is write a joint distribution with a backward kernel which does not depend on x0 here, because we don't have access to it. So what we're going to do is simply write for this quantity the exact same form as this one, where in mu k here we replace x0 by an estimate of x0. So this is an intuitive proposition. What we're going to do is here propose a backward Markov kernel where for this quantity we use the bridge of the Einstein-Uhlenbeck where x0 has been estimated, and to estimate it we're going to plug any neural network that we want to work with. So we can derive an explicit form for this estimate. This is just using a Gaussian conjugacy. And you can end up at each time with the estimation at time k plus 1 of what is your data at time 0. So what you need to train is this neural network, which takes as an input the current noisy data, the time step, and wants to predict what's happening at time 0. And to learn it, usually, I don't know, yes, I was not sure I described it. What you do is, there are two ways of training this kind of neural network, either by score matching or a variational inference. And you end up with this kind of optimization processes where you can understand this E theta, this neural network you're training, as the noise you should add to x0 to obtain xk. So this is briefly what you can, how you can, I try to sum up what people do in diffusion processes in 2 or 3 slides. But basically what you need to keep in mind is that it's hard to use this thing. Okay. You start by sampling data from your data set, then you blur everything up to obtaining a Gaussian, and then what your objective is to start from a law that you know, which is a standard Gaussian, and revert the process. And to do so, you try to propose a Gaussian kernel which mimics the Gaussian bridge. And you train it using any kind of neural network you want. We won't get into the details of this, the networks you can choose. I have no idea how you should tune it or optimize it. It's quite complex. And here, if you just want to have a nice illustration of what's happening, not using images, but distribution that you know, pi0, we assume here that it's a Gaussian mixture, which is an example that Yazid used a lot during his PhD. So he liked to test every fancy method only using Gaussian mixtures, when we have surprise all the time. So it's pretty interesting to do so. And what you have on the right, on the left-hand side is the true data you want to sample. And on the right, we are going to sample, so n here is 500. So at time 500, you sample center the Gaussian and standard. And we're going to go backward in time. And here you just see, I don't know, 100 samples from the marginal distribution, which goes backward in time. And what you can see is that once you've trained your model, you recover at time p5 here a distribution which looks similar to what you wanted to do before. Obviously, it's easy to do in this case and much easier than doing this for the images, but it's still pretty interesting to do this in this case just to check that everything works well, and in particular that for a multimodal distribution you can recover all the modes and you're not sampling anywhere over there. Which is not the case for all the methods which have been proposed using diffusion processes. So it's still not this easy to tune these methods to make them work even on easy cases. And just a quick word to explain why these methods are popular. So I don't know when was the first paper on this, but maybe 3 years ago, something like this, 2020 or 19. The first results we had were not, when I say we, it's the team around Valentin de Bortoli for this kind of results. What you can prove is that the people using quite strong assumptions on the true data distribution are able to have upper bounds between on the total variation distance between the true data and p theta 0, which is the marginal at time 0 of your joint backward distribution, which is your estimate for pi 0. What they obtain is a sum of error term, which depends on the mixing time for the process to converge to the stationary distribution of the noising process, and which depend on mainly on the Euler discretization of the backward process. And what you can see is that you've got a quantity m here, which depends on the quality of your neural network. Does the neural network approximate well the true score of the data? And other quantities which depend on n, which is the total number of time steps you use. And as you can see, you've got this term which you can control easily, and this term which is explosive. And it's explosive because of the assumptions on the score, which is assumed to grow polynomially. Yes, this is what I wrote. And this comes simply from the application of Grandval lemma to control the Euler discretization moments of your Euler discretization. And much more recently, so a few weeks ago, a few months ago, Alain Durmus and his co-authors showed that only using really weak assumptions on the true data, you can obtain upper bounds which are controlled exponentially fast on the total number of time steps. You don't have this term anymore. So this justifies the use of diffusion models to approximate pi 0 by p0 theta. So once here you've trained your neural network, you've got p0 theta, which is an estimation of pi 0. And what you can do is sample from p0, but you cannot evaluate it because it's a marginal distribution of joint process. So it's you know it in an integral form. Or maybe I'm gonna, well, I don't need to skip these examples since I still have 30 minutes during this talk. So here, this is another example, which I'm gonna go back a bit later just to explain why the problem is hard. So one of the main focus that Gabriel and Yazid worked on during the experiment was to solve in-painting related problems where you observe only a part of your data. So for images, you can think that you removed part of the image and you want to recover what you removed. And here, in this case, you can assume that in a two-dimensional setting, you only observe one coordinate of your process. So this is y is the first coordinate of a two-dimensional vector. You have y here, and what you're going to sample is not a two-dimensional distribution, but a distribution which is supported by the real line. And this is a hard problem, as we're going to see in the experiments. So now we're going to go back to our Bayesian posterior estimation problem. In this setting, so what you can remark is that our target, which is not pi 0, but p0 theta weighted by g0, which in our case is a linear observation model, you can write it as a marginal, proportional to a marginal distribution, which is simply your backward process that you've been that has been integrated out from time n to time 1. So here, this quantity is only the joint distribution of the x from 0 to n that you've integrated to obtain p0 theta. So you can write this quantity, but obviously you cannot evaluate it, and this is going to be our problem. So it's not structurable, and it cannot be easily approximated. So maybe Nicola will have a few ideas, but even using standard SMC is not easy to plug it in this setting. So what we're going to do instead is we've got this G0, which is given by the problem. So this is our observation model. What we're going to do is introducing a sequence of potential functions, the GK, and we're going to build artificial posterior distributions from time n to time 0. So Pn and here pk are just the marginal of our backward process. So for Pn it's easy, it's only the standard Gaussian, multidimensional standard Gaussian. And instead of sampling directly from this, we're going to try to solve a Bayesian posterior estimation for this time. We are not really interested in the solution of this, but if you build this recursion, which is really easy to write, you can directly see that you have a recursion between phi k and phi k plus 1. So if you have a good approximation of your posterior at time k plus 1, you can hope that you will have 1 for time k. And this identity helps you understanding that you recover at each time what you build as an artificial posterior problem, which is the marginal at time k of your backward process weighted by a gk. And if you do so from time n to time 0, in the end, you're going to recover phi 0, which is what we want to obtain. So you're going to get rid of all the samples or approximation of the phi k. These are just instrumental proposal distributions, but you will end up with an approximation of your target quantity. And with the idea that we're going to use, as we've got pk here, we're going to use the whole framework of diffusion processes, because we're going to need samples or something related to the samples we've built from time n to time 0 to obtain our estimation. And what you can do is you can rewrite your target at time k. So this is the recursion. Here, you introduce simply the backward kernel to see that you can write your posterior at time k as a function of your posterior at time k plus 1. Here, transition kernels that we're going to use within an SMC procedure, as Nicola explained this morning and yesterday. And here there is a weight, which is usually hard. So if you don't make any assumption on the G, it's something that you cannot compute. So you're going to add on top of everything the fact that this quantity cannot be evaluated. But in our case, as we can use Gaussian conjugacy, these quantities will be available in closed form. So what we're going to do, here you can see that you've got something to go from k plus 1 to k. We're going to use a proposal kernel, which is this guy, to sample from individuals we've got at time k plus 1, individuals at time k, plug them in this recursion and weight them exactly as Nicola explained. So I did not prepare any slides for the SMC, as you're all experts on this now. thanks to Nicolas. So thank you, Nicolas, to help me with this. So if you sum up, so the framework is pretty complex, and there are many notation in the SMC literature and in the diffusion models literature. But in the end, the overall procedure can be written in like 3 or 4 lines. So if you want to sum up everything, you only have to choose what is going to be your family of potential function G, and then you only have to, starting at time n, you're going to sample from typically, you can, this is not what you're going to do, you're going to want to do, but you could even sample from Pn and weight using Gn, and then backward in time, you're going to sample from this transition kernel and weight using the weight W that we wrote. So what you obtain, so here we go back to the mixture of Gaussian densities, and in this setting we can compute everything explicitly. So when I say we, once again it's Gabriel and Yazid who did all the computation. What you can see is that instead of, for now, trying to sample from phi or have an SMC estimation, we can directly, using this potential, show what exactly is phi k at each time k. So in this case, obviously it's a toy example, but you can see what are the artificial posterior you build from time 450, I don't know why this number, to time 0. So the idea is that we're going to show that the green individuals, they are really sampled from the true posterior, and you can see that the family of artificial density you're creating really target, here we stop at phi 2, and we target these kind of samples. So the idea here obviously is not to say that we know how to sample from conditional Gaussian distribution, it's not really interesting, but to see that when you introduce this kind of, this kind of artificial phi n, phi k plus 1 up to phi 0, indeed what you're going to do is sampling from distributions which are closer and closer to phi 0. So obviously you need a bit of work to do this in more general settings, but at least it's reassuring to see that in this setting we recover exactly what we wanted at the beginning. The problem we have for more complex settings is that we're going to need to use SMC procedures to sample individuals at time k using the individuals we had at time k plus 1, because we don't know how to sample exactly from the recursion we wrote 2 or 3 slides ago. So this is the SMC procedure. So the only thing you do is, assuming that at a time further in the future you've got a family of weighted or uniformly weighted particles, which are approximation used as an approximation of a phi t plus 1. You plug this approximation in your target recursion, and you can find what is going to be your new target at time t, the quantity you want to sample from, and this you can do using any of the methods that Nicolas detailed this morning. And then what you're going to do is select people from time t plus 1. So for each new individual at time t, you first sample from your pool of candidates at time t plus 1, and then to create a new guy at time t, a new girl, you just sample from a pt y. And then you obtain your recursion and your phi t n up to time 0. So there are a few details that I just put under the rug. I don't know if you can say this, but mainly here you've got the whole idea on how you can use Monte Carlo diffusion processes to solve Bayesian problems and to combine with SMC procedures. And what you can obtain, so here it's not something which is, I don't know, it's not, for people who are used to SMC literature, this kind of results you can obtain are pretty standard. So you're going to make assumptions on the way you propagate particles and on the weights you assign to each particle. So basically, if you can control the weights, I'm not sure it's written, yes, it's written here. If you can control these quantities, you will recover standard results like inequalities like this. So you can see that here this is your true, not your true target, it's your fake target where you replaced pi0 by p0 theta. You can see that you've got an exponential decrease in epsilon here. The trick is that these quantities depend on n, obviously, and controlling this is a bit trickier. And this, so according to Yazid, we can get rid of this quantity, but we've got here also control on the bias between the Kullback. So the Kullback here, it's a way to control the bias of your estimate, because here you compute the expectation on all the particle cloud. So the expectation here is over all the xi's and W and I, so all the indexes you've sampled from the particle cloud, and you can see that it decreases in capital N. The problem, so your number of particles. The problem here is that this quantity depends on N, and it's not this easy to prove that it grows not more than linearly. So with strong assumptions, we can show that it grows linearly in N, but with weak assumptions, it's not easy. While in standard SMC literature, we know that at least for filtering problem, without too strong assumptions, we've got control which are in time over number of particles. Okay, so now, oh, sorry for that. A few experiments. So as you understood, I didn't run the experiments, so I won't talk too much about it. I guess the interesting thing, in my opinion, on this is that, so first, it's always using a toy example where we know the truth. So in this case, it's a mixture for the top one, it should be the mixture of Gaussian, and here it's a funnel distribution, which is another standard toy model to test generative models. The interesting thing is that if you, whatever the dimension you use for the data and the observation, what you can see is that these methods, so this framework of building fake targets backward in time, but using the powerful SMC strategy then to approximate them, leads to metrics which are way better than all the competitors. It's not interesting in itself, we don't really care about being better, but the interesting thing is that if you have a look at the samples from the other algorithms, what you can see is that even in the case of mixture of Gaussian, these algorithms are going to forget some modes, so they don't cover all the target distribution, or going to sample in regions where you don't have mass for the true targets. So it's interesting to see that using our SMC approach, we use well-grounded methods to make it work, and it's kind of reassuring because it's not easy to have the same conclusion when we are working with images where metrics are not this easy to compare. Okay, and here it's just for fun. I guess you cannot have a talk on diffusion processes without this kind of pictures where you can compare different methods. So MCG-diff is for Monte Carlo guided diffusion. So this is a method proposed by Gabriel and Yazid. And you can see what's recovered by our method and what's recovered by the other. What you can bring with this, I'm not sure, so I don't want to, it's not because I didn't run the experiment, even in other papers, okay, we can sample the cats, heads of celebrities or whatever. Did we cover really the prior distribution? I don't really know, and this is not really the interesting thing in my opinion. But at least if we use the standard metrics and sampling experiments than the other did in diffusion papers, we end up with a nice competitive samples. It remains a lot to do. So here what we can bring back from this is that the tricky thing and the interesting part was to design a well-suited sequence of potential GT to build our posterior proposal. Once you've done this, you can use whatever you like in the SMC family. So once you've done this choice of GT, basically all the work is done, if you have a look at it from far away. The problem here is that we are going to end up with a few theoretical results which are quite incomplete. So here is a list of things that should be done. Here I only talked about linear inverse problem because we can compute everything exactly. So all the integrals, all the weights can be computed exactly, which is not the case for nonlinear settings. So you should add an additional estimation layer to your process if you are in a nonlinear setting. And maybe what would be very interesting, I guess, is this last part, in theory at least, is to extend all the results with respect to the true target. Here what we can prove is that you need to believe that your prior distribution is well estimated because we're comparing our samples to a fake posterior, which is the p theta 0 times g0. So what should be done now is to extend the results that others did, like the paper by Dirmus and his co-author, to extend the control on the distance between pi 0 and p theta to the controls between the posteriors at time 0. I guess this would be a nice theoretical contribution. And I guess I'm going to stop there. 45. Great.